Ho! This is AP Calculus Lecture 1.4b. So we are going to be working example problems from page 76 in the textbook. This lecture is called Continuity and Discontinuity. It's a pretty short lecture overall. I want you to go ahead and draw a graph like this, similar to the graph that we had in the last lecture. Make sure you put a point right here at C and S, so that's a little different. You've got a couple of holes here. So just go ahead and pause the video and draw that out. All right, so I'm going to make this right here is a break, right? So we can call that a jump discontinuity. So the graph literally jumps if you're going left to right. This is a hole, and that's called a removable discontinuity. All right, this jump discontinuity would be non-removable. So some notes to go along with this graph. A function is continuous at a given point if it has no jumps or holes or even asymptotes at that location. So an asymptote, I didn't put an asymptote on this graph, but an asymptote would also be a discontinuity. So no jumps, holes, asymptotes. All right. But a hole is a different kind of discontinuity than a jump. All right. So let's make, a rule about discontinuities here, or write that down. A function is continuous at a point C if, I'm going to make a couple of columns here. So let's make a continuous column and a not continuous column. So I'm going to give you the first rule to be continuous is that f of c has to be defined. So remember, we're talking about continuous at a point C. So f of c has to be defined. So what's an example of a discontinuity at C? Well, something like this. If you had a hole at point C, then that would not be continuous. A hole is undefined. That means there's a zero in the denominator there. Okay, so a hole, even though you can take a limit there, a hole is a discontinuity. All right, rule 2. The limit as x approaches C exists. Okay, well here the limit would exist, so you would also, to be continuous, you can't have a situation like this. So your fingers, as your fingers approach point C from each side, they don't come together, do they? So that's an example of the limit of as x approaches C doesn't exist. and here we're undefined at C. And then the third thing that has to be true for a function to be continuous is that the limit as x approaches C of f of x has to be f of C. All right, so maybe drawing what wouldn't be continuous there would help. So for example, let's say we had this, and then at point C we put a point there, and this is point C. So in this particular case, the limit is going to be up here. So f of C does not equal f of x. This is f of x, but the limit would be here. Okay? So that would be a not continuous situation. So you have to have all three in order for a function to be continuous. So a function is continuous, basically, if there's no holes or anything, no holes, no jumps, no asymptotes, that's continuous. You know, the graph part of it's pretty simple. All right. Pause if you need to and write a couple more notes. All right, a continuous function is continuous at all points. So that's what I was talking about just a minute ago. It's just a curve, right? No holes, no jumps, no asymptotes. So continuous at all points. All right. If the limit exists at a point of discontinuity, okay, so we can take a limit, it is a removable. So there's two different types of discontinuities. A removable discontinuity. So if the limit exists, if you can take a limit, so basically what we're talking about is if it's a hole. All right. If the limit does not exist, it is a non-removable discontinuity. Okay, so let me draw out removable would look like this. That's removable. That's removable. So these violate rules 1 and 3, okay, from the previous, violate rules 1 and 3, but not rule 2. Okay, from the previous, from a few minutes ago. Okay, also if you take a limit, if you plug the number in, you're going to get 0 over 0 form. So we can do more work and remove the discontinuity. So that's what we've been doing a lot of. Plug it in, try to get the limit. Discontinuity. That is not how you spell discontinuity. Discontinuity. I left off a lot of letters, didn't I? All right. Non-removable. So that's going to be something like this, a jump or an asymptote. Let's see, an asymptote, remember that from pre-cal, you have an asymptote. Let's say you have a function that's at point C. That's a discontinuity, that's non-removable. You're going to get, this violates all three. And this is where you would have non-zero. So you plug the number into the function over 0. So you can't really do any more work in that case. All right, let's do a few examples and then we will be done. Okay, we are on page 76. Let's do example 28. All right, looking at example 28, it's just a graph there. And it says find the x values at which f is not continuous. Well, you can see the only place it's not continuous is at the hole. Okay, so that's at x equals -1. So it's discontinuous at x equals -1. Easy peasy, right? So let's look at 31. So that one says find the x values at which f is not continuous and which of the discontinuities are removable. So we have f of x is equal to x squared minus 2x plus 1. Now, see if you can remember, what shape is this? All right, that's just a parabola. There's no denominator. So there's no place where there's no asymptotes, no place where it's undefined because there's no denominator. So this one is continuous at all points. It's denominators that cause all the trouble. All right, so function like that, you're good to go. All right, let's look at 38. So the same set of instructions, and this time we have f of x is equal to x minus 3 over x squared minus 9. Well, let's factor that denominator. So we'd have x plus 3, x minus 3. We want to, there's two possible discontinuities here. There's wherever the denominator is 0. So at x equals -3 and 3, right? -3, that'd make the denominator 0, 3. Both make the denominator 0. So what we have to do is take the limit as x approaches -3 of this function, of x minus 3 over x plus 3 times x minus 3. So we can cross that out as long as x does not equal it does not equal 3, right? Cross that out, and then we have the limit as x approaches -3 of 1 over x plus 3. That's going to be 1 over 0, so that does not exist. So negative 3 is non-removable. So we have a discontinuity at negative 3. It's non-removable. Let's look at the other one. As x approaches 3 of x minus 3 over x plus 3 times x minus 3. So again, we can cross out x minus 3 as long as x does not equal 3. And that's going to be the limit as x approaches 3 of 1 over x plus 3, which is 1/6. So we got an answer on that one. So you could take a limit. So 3 is a removable discontinuity. So we have a discontinuity at both 3 and negative 3. It's where the denominator can become 0. But negative 3 is non-removable because we got a limit does not exist. 3 is removable because we actually can take a limit there. So that means at 3 there's a hole. All right, and negative 3 there's a jump or an asymptote or something like that. All right, we're pretty close to being done. Let's take... So let me go ahead and give you a note, and then we'll do one more example. So what you have to do on that previous one, so just write this right underneath, is take the limit at the points that make the denominator 0. So in the example's case, it's 3 and negative 3. Now let's say you get a piecewise function. So for piecewise functions, take the limit from each side to see if equal. If they are equal, there's no discontinuity. If they're not equal, then the limit does not exist, so that would be non-removable, right? Okay, let's do an example of a piecewise function, number 44. So that one, we have f of x is equal to negative 2x plus 3 for x less than 1 and x squared for x greater than or equal to 1. So what are we going to check? At what x value are we going to check to see if there's a discontinuity? Well, there's only one spot there could be a discontinuity. That's at 1. Okay, so let's take the limit as x approaches 1 from the left, because it's less than 1 right here, of negative 2x plus 3. So you plug in 1, negative 2 plus 3 is 1. And we'll take the limit as x approaches 1 from the right of x squared, plug in a 1, and you get 1. So they are equal. So it is continuous. All right, so on that one, there's no discontinuity. Okay, the homework. So we start on page 76. It goes into 77 just a little bit. So the homework is 27, 29, 30, 32 through 37. Do all of those, not just the odds. 39 through 43. And 45 and 46. All right. And it shouldn't take you too long. Some of these are graphs and you can just easily read them. So good luck on that homework, and I will talk to you on the solutions video.